Young's modulus. What is it? Well, Young's modulus is also called the modulus of elasticity. And basically it says if you apply a force to it, how much is it going to stretch? So how stretchy is the material? So Young's modulus is going to be E. Use the symbol here, Young's modulus. And it's related to two things. It is related to the stress. How much force you're applying per area. What's the pressure in the material? Stress, and that has units of newtons per square meter or pascals. It is also related to the strain. How much it stretches. So this is going to be the strain. The strain has no units. So this means that Young's modulus is going to have a unit of newtons per square meter or pascals. And so yes, we have the stress, how much force we're applying, how much it stretches. So for a given force, as you can see, if the Young's modulus is big, it does not stretch a lot. But if it's small, it does stretch. So the strain, the stretch, is going to be related to stress over Young's modulus. So if this is a big number, stretches a small amount. If this is a small number, stretches a big enough amount. So steel or something like that, Young's modulus is going to be in the gigapascals, or hundreds of gigapascals range. Something like a rubber band, maybe in the 100 of megapascals. So the lower that number is, the stretchier the material. The bigger that number is, the stretchy material. So let's try and find a example that we did earlier. So a 2000 kg weight is on a 25 millimeter diameter cable. Cable 20 meters long. It stretches 4 millimeters. What is Young's modulus? Okay, so what's this going to be? Let's go work it out. So Young's modulus, E, is going to equal the stress over the strain. So let's draw a picture. We've got a 20 meter long cable. We put a couple of thousand kg on it, 2 ton. And so it's 20 meters, and it stretches 4 millimeters, so 0.04 meters. So the question is, if we're going to find out Young's modulus, do we know the stress? No. But can we work out the stress? And the answer of course is yes. So stress is equal to force over area. Which leads to the next question, what's the force? Well, force is going to equal mass times gravity, which is going to equal 2000 kgs. And we're going to use 10 meters per second squared here, because we're just using a demonstration, equals 20,000 newtons. You can use 9.8 if you want. So we know the force, so stress is equal to 20,000 newtons. Do we know the area? Well, area is equal to pi over 4 diameter squared, using the engineering system. It's equal to pi over 4, 0.025 meters squared. Remember what we do is we take the cross-sectional, if the force is this way, then we take the cross-sectional area across there. So We work out how much steel is holding that weight. Pi divided by 4 times 0.025 squared equals 4.908 times 10 to the negative 4 squared. Does that seem reasonable? Yep. Okay, so 4.908 times 10 to the negative 4 meters squared. So we go 20,000 divided by 4.98 equals 40.7436 what's that, megapascals. So 40.74 times 10 to the 6 pascals. So we know the stress, so stress is 40.74 megapascals. Do we know the strain? Well, we can work, no, but can we work out? So the strain is going to equal change in length over the original length, which is equal to, well, it stretches 4 millimeters. 4 millimeters is 0.04 meters. Over, how long is the cable? 20 meters. Equals 0.0002. Remember, strain has no unit. So divide by 0.0002 equals, so we go divided by 0.000. How many? 3. Yeah. 2 equals 203.7 gigapascals. Does that seem reasonable? Well, structural steel is about 220. So yeah, I mean, that seems like a perfectly reasonable argument. So what we've done is we've got a 20 meter steel cable. We put 2 tons on it. It stretches 4 millimeters.